Here is the next example. I'm going to do the AC analysis, also called small signal analysis of a transistor. So here is the given circuit. In this circuit, I think you can see it clearly. In this circuit, find out whether this is CB configuration or CE configuration or CC configuration. So here is my base, here is my emitter, and here is my collector. So output is, so wherever you see V naught, that's output. Output is connected to the collector. So that's not a common terminal. And input, always V signal, which is connected to the base. So base is not a common terminal. So definitely this is a CE configuration, common emitter. So that emitter terminal is the common for both. Now here, while doing AC analysis, I mean, if you have a capacitor connected to the emitter, that means while doing AC analysis, this capacitor is going to act like a short circuit. Okay. So while doing AC analysis, emitter is directly grounded. We can use the pi model. That makes our calculations simple. Now, the first part, what I'm going to do, I'm going to remove, I mean, we have to do the DC analysis. So in DC analysis, what I'm going to do, I'm going to replace these two resistors on the base and that voltage source into a single source with single resistor. So while doing this analysis, this is what I have: 10 volt and 40K, another 40K. Now I need this voltage as VBB, and I mean, while finding RBB, remove the all independent sources with their internal resistance. That way we can find the RBB. So here I can see RBB equal to 40K parallel with 40K. This must be 20K. And VBB is 10 volts is going to divide equally across 40K and 40K. So, or you can use the voltage division rule. 10 multiplied by same resistance divided by total resistance. Okay, so that will be 5 volt. So I'm going to redraw the circuit diagram. So my circuit is going to be, I mean, I'm still doing the DC analysis part. So in DC analysis, I will have a 20 kilo ohm resistor and 5 volts on the base. That's an NPN transistor. Based on this arrow, you can tell that's NPN. That's 4 kilo ohm, 5K, and 15 volts. Now I'm going to use the KVL in that loop. So here is my KVL. So minus 5 plus 20K IB. The current passing through this is IB, and there's a voltage drop across this, assuming this transistor is working in active mode of operation. So 20K IB plus 0.7 plus 4K IE equal to 0. The current passing through this is IE equal to IE. Do not remember what is the beta value, but time being, I'm going to take that as 100. Okay. That value is given by the manufacturer. So in the questions, definitely I will provide that beta value. So can you guys give me IE or IC value from this? I'm going to pause recording. So here we found the IC value as 0.71 milliampere. I substituted beta equal to IC over IB. You need to remember this formula. Same thing with alpha equal to IC over IE. And we know that relation between alpha and beta, alpha equal to beta over beta plus 1. Now I found IC, we'll find IB and IC, so that way I can find whether this transistor is in active mode of operation or not. VC and VE. So all I need to do is find VC and VE and verify whether that transistor is in active mode of operation or not. Okay, sorry, looks like I made a mistake here. So 200K divided by 100, sorry, 20K divided by 100 is going to be 200 IC. And it's 4,000 divided by 0.99 equal to 4.3. So IC end up with 1.01 milliampere, not 0.7, as I mentioned in the previous case. As I mentioned. So IC, we found that 1.01 milliampere. Now I'm going to find IB. IB must be based on this IC over beta. IC is 1.01 or beta is like 100. So it's going to be 0.01 milliampere. That's my IB. Now, do I need IB? I mean, it's not much useful. I'm going to find IE. IE must be, you can use IC plus IB, or you can use alpha and find that value. Since I already found IB value, I'm going to use that. So it's going to be 1.01 plus 0.01. So it's going to be 1.02 milliampere. Now I'm going to find VE, voltage at that point. VE equal to 4K times IE. Okay, so 4K times 1.02 milliampere. Approximately, how much is that? That's 4.08 volt. That's my VE. I'm going to find VC here. VC equal to 15 minus 5K times 1.01. So this is approximately 10 volt. Okay, so VC equal to 10 volt. VC equal to 10 volt and VE equal to 4.8. So VCE equal to VC minus VE, which is way greater than 0.3. So this transistor is in active mode of operation. Please write it down here saying that VCE is greater than VCE saturation. Okay, so this transistor is in active mode of operation. So it's working in active mode. Now we're going to do the AC analysis. While doing AC analysis, I mean, since emitter is grounded, we're going to use the pi model. If emitter is not grounded, then we'll use the T model. Okay, so as mentioned, since emitter is grounded while doing AC analysis, we're going to do this example by using the pi model. So this is the equivalent circuit of the pi model. RBB, what we have, RBB is 20K. So this value is 20K. What is the R signal? Here, he didn't give any R signal resistance. So saying that, assuming that the signal doesn't have any internal resistance there. So I can ignore this. So this value, I can take it as 0. How about RC? I think he gave this value as 5K. RL, is it RL is also 5K? Yep, RL is also 5K. Okay, now these are the formulas you need to remember. R naught equal to VT over IC, R pi equal to beta over GM, GM equal to IC over ET. So IC, we have 1.01 milliampere. So GM equal to 1.01 milli, VT is 25 millivolt. Okay, that's the thermal voltage. That value is around 25 millivolt. So based on this, this is going to be 0.01 ampere per volt, or Simon is the another unit. It's called transconductance. Now R pi equal to beta over 0.04. Beta we have 100 and GM equal to 0.04. What is this value, guys? Approximately 2500 ohm. Now R naught equal to, that's the internal resistance of the transistor. That's VT over IC. VT usually given by the manufacturer. That's 100 over IC is 1.01 milliampere. So this is approximately 100K. This R naught is always connected between the collector. So here is my collector, this is my base, and this is my emitter. This is connected between between the collector and emitter. So instead of grounding it here, I just grounded it there. It's the same thing. Now our goal is, if it is pi model, it's real easy. Okay, here is my input circuit. That's my V input, and output is connected right there. So here is my V output. Yeah, R not equal to not VT. It's another error there. It's VA over IC. And VA value is given by the manufacturer. Actually, I used VA there, 100 volts. This 100 volts is VA, not VT. Okay, thank you for correcting me, Adam. Okay. So once we have all these values, this is the pi equivalent circuit. Now our goal is finding the AV, voltage gain at load. So AV is nothing but V naught over V input. So all I need to do is find the relation between the output and the input. So AV with load. So with load, if you can look at here, all these three are connected in parallel. R naught parallel with 5K, parallel with RL. Okay. So R naught, RC, RL are in parallel. And what is the current passing through them? That must be, this is the current, GM times VB. So basically this ground is connected all over. So GM times VB is going through all these three resistors. So I can combine all those three, and current is entering here, leaving there, but I want V naught at the negative terminal. So my V naught equal to, from there, from here, I'm going to write it here, from V naught equal to, I can write that as GM times VBE and R naught parallel with RC parallel with RL. Okay, so 5K parallel, which is 2.5 kilo ohm, and 2.5 kilo ohm parallel with this is 100K. Can you guys give me that value? Approximately 2,300 or 400. Okay, so we know that. I know GM value, and I know VBE. VBE is the voltage drop across R pi. But at the same time, the voltage at this point and this point are same. The voltage here must be VN. Okay, so the negative point I'm showing, that's across the ground. So this is also grounded. So I can say my VBE is same as the V input. I'm going to replace VBE right there. So V naught equal to GM times VN, and RC parallel with RL parallel with the R naught. Okay, so AV is nothing but V naught over VM. I mean, AV is nothing but V naught over V input equal to GM times RC parallel with RL parallel with R naught. Okay, so some people might say, okay, I'll go ahead and copy this equation and I will substitute it. Is it going to make any difference? No, you don't need to show me this step, or you don't need to show me this step either in the exam. But remember, sometimes there might not be R naught, sometimes there might be some other elements. Okay, so instead of using this formula, I highly recommend you to analyze the circuit at that time. Okay, now AV naught is nothing but the gain with no load. So what I'm going to do, I'm going to replace or remove the load resistance RL. So AV naught equal to V naught over V input at no load. Okay, that's going to be GM times RL parallel with R naught. That's my AV naught. By the way, remember, we end up with this V naught as this as a negative value. I forgot to indicate that, because remember, current is entering here, leaving the negative terminal, but I want the voltage at V naught. That's going to be negative terminal. So this must be a negative. So V naught equal to minus GM times VBE times R naught parallel with RC parallel with RL. Okay, so this must be a negative value too. So that is the reason if it is CE configuration, your output is going to be inverted. So, I mean, if your input is, say, for example, 1 sine omega t, your output based on this, I can tell the output is approximately 100 times more than the input. So it's 100. So negative V input times GM times, I'm looking at AV, GM times RC parallel with RL parallel with R naught. Okay. So if your input is something like this, 1 sine omega t, my output, so this is time, that's my input signal. My output signal is going to be inverted, something like this, but it's 100 times, I mean, whatever that factor is, magnification factor. Based on that, you can tell. Okay. Okay. So here there is no signal resistance. So GV overall gain is output over input, which is V signal. I can write this as V naught over V input times V in over V signal. This V in over V signal. So here is my signal. That's my V signal. That's my R sig. R sig. And here is my input terminal. So here is my V input. And all of this transistor input, I'm representing this as R input. Okay. So based on this, I can tell V input equal to V signal times R sig over R, sorry, this is R in over R sig plus R in. Same resistance divided by total resistance. Okay, so if I substitute this equation in there, my overall gain must be AV times R in over R in plus R sig. This formula is not going to change either with pi model, T model, or CE configuration, CB configuration, CC configuration. This equation is same for any configuration. Okay, so here R signal is 0. So basically your GV equal to AV. Now, what is the input resistance and output resistance? Okay, so input resistance, when we look at the circuit from here, okay, from these two, this and ground. So the resistance I see between these two is these two are the resistors, RBB and R pi are the two resistors I can see from the input side. From the output side, I see R, I mean, when we are looking from output sub point of view, you're assuming there is no load connected. Okay, that's how we find the output resistance. Same thing with the input resistance. We'll remove all the source. So when we're removing the source, that R sig is also going to go away. So from here, my R input signal, R resistance, input resistance of that whole circuit is RBB parallel with R pi. That's one thing, input resistance. And the output resistance equal to R out. This R out is the output resistance of the whole circuit. The small R out is the internal resistance of the transistor. Okay, so R out, we're looking from this, that's going to be R naught parallel with RC. That's our R output resistance. So that's it. I'm going to stop recording this video.